Stefano, thank you very much for the kind introduction. Talking about alternative fuels, I think Andreas outlined quite well why do we actually need alternative fuels for the medium speed sector. But of course, the first question arising is what would be an alternative fuel and what would be conventional type of fuel. Yeah? This slide shows you simplified production pathways for the majority of fuel types. And in general, what you will need for all fuels is, of course, an energy carrier or energy source and possibly a carbon source. And with that, two things, you can pretty much make every fuel from both fossil and renewable resources. Overall, there's not the one and only definition, but the major concern is that conventional fuels are fossil-based liquid fuels like gasoline, kerosene, diesel, and also HFO and MFO, maybe also natural gas and even LPG, but for the latter ones, the overall number of applications are currently still rather limited. Everything else then what just mentioned would someone classify as alternative fuels, yeah, both from fossils and from renewables. Looking at fossil fuels, liquid fuels derived from coal and natural gas would be called kind of synthetic fuels. Biomass-derived fuels are quite widely known already, but also there we have quite a bunch of different types of fuels. So you can take, for instance, the oilseeds. From the oilseeds, you can make hydrated vegetable oil, HVO. Bioesterification, you can produce biodiesel, RME, or palm seed methyl ester. You can take starch and sugar cone and make quite easily alcohols, yeah, ethanol via fermentation. You can produce alcohols also via or from lignocellulosic material. This is currently also starting to ramp up, and via anaerobic digestion, you can produce biogas. And biogas is mainly consisting of methane and carbon dioxide. And then via biomass gasification, so producing synthesis gas, you can also produce other hydrocarbons, for instance, via the Fischer-Tropsch process. E-fuels is what currently pretty much everybody is talking about, and the main characteristics of e-fuels is that the basis for all e-fuels are green hydrogen, what is derived from water electrolysis by means of renewable electricity. And then by combining the green hydrogen either with carbon dioxide or with nitrogen, you can produce pretty much all types of molecules what might be suitable as fuel for internal combustion engines. As indicated, there is not the e-fuel or not the one synthetic fuel. So you can really produce quite many different molecules what are suitable as fuel. But what they all have in common when produced from renewable sources is that they typically contain no or only extremely low amounts of sulfur. And because the share of high boiling components or aromatics is also significantly reduced, usually all that types of fuels combust significantly cleaner than the fuels we are using currently and today. I now briefly talk you through the different fuels that seem to be most promising for medium speed applications. And then my colleague Anne Gooden later on is going to talk a little bit more about thermodynamics and specifications of some of these fuels. So starting with hydrogen, that of course is the most simple e-fuel if you want to. And talking about green economy, hydrogen will for sure play a very important role in the future, and not only for energy storage in the grid, but also for mobile applications. Japan announced that they will import very large amounts of hydrogen from Australia. So it's not a surprise that Kawasaki is planning to build a deep sea going liquid hydrogen carrier, that it's also then going to be operated with liquid hydrogen. And the world's first hydrogen-powered vessel will go into operation by 2024 from the consortium with Orca powered by nature. Since hydrogen is required for all e-fuels we can produce, it's obvious that there's no e-fuel that can be produced at cheaper costs than hydrogen. Given the PV electricity price we currently see in Saudi Arabia, with even below 1 euro cent per kilowatt and per kilowatt hour. Current estimations for hydrogen costs are in the range of €1.50 to €1.44 by 2030, and that would be even cheaper than fossil hydrogen we have currently mainly from natural gas. Overall, hydrogen is currently widely used. For in steel plants, for instance, as reducing agent. The process how to produce it is also widely known and quite robust already. And that's all on the good side, but of course there's always a bad side. And for hydrogen, it is the extremely low energy density. Andreas touched on this briefly in the previous presentation. Even when liquefied hydrogen at minus 250 degrees C, energy density or volumetric energy density is still 5 times lower than that of HFO. Sorry. If you would translate that to a deep sea going 15,000 ton vessel, that would relate to roughly 10 to 11% less loading capacity, because it's not only the fuel volume as such, but also the insulation of the tanks and so on. And this also will increase the ship's cost by about 10%. So really significant differences compared to conventional diesel powertrain. Still, we believe that hydrogen will play an important role in future mobility systems. Also, it's one of the fuels that definitely have zero CO2 emissions at the tailpipe. The other fuel that is inherently CO2 free while combusting is ammonia. And also ammonia has been used already as fuel, mainly during World War II, not because it's the perfect fuel, just because there hasn't been any alternative at that time. And due to its ignition and combustion characteristics, it requires a sophisticated ignition system, such as dual fuel. I think Arne will touch on this later on in a little bit more detail. And moreover, due to its quite low flame speed, it's also not suitable for applications with very high resolutions, but rather medium speed or even low speed applications. In fact, ammonia is pretty much a hydrogen carrier, since nitrogen itself doesn't take actively part at combustion. So ammonia is, of course, a little bit more expensive than hydrogen, but cheaper than some other e-fuels. And the reason for this is that hydrogen subtracting or air separation is way easier if you have 70% nitrogen in the atmosphere rather than 400 ppm carbon dioxide. Currently, ammonia is produced in the megaton scale already, and it's mainly used as fertilizer. It's shipped around the world. So infrastructure would be available, but the downside for ammonia is mainly its toxicity, and already very low concentrations of about only 20 ppm are toxic for human and sea life already. So there are quite high requirements for safety installations and handling. So ammonia might be an interesting option for large applications or mining sites, for instance, with its own fuel production, far away from civil population. And initial engine tests are currently ongoing at full engine test sites. But of course, there are also some pilot and demonstration projects ongoing, such as this ammonia and hydrogen fuel tractor operated in a farm in the United States. They synthesize the fuel pretty much all electric on their own farm, making use of a conventional Haber-Bosch process, so the way how you do it in industrial scale already today. And the ammonia was not used as a fuel on the farm, is then directly used as fertilizer for the crops. The tractor you see on this picture over here runs on hydrogen and ammonia, spark ignited. And as you can see, it requires quite a lot of additional fuel storage volume. We talked about energy density of hydrogen already. Also, the energy density of ammonia is roughly 1/4 of conventional diesel fuel, even in liquefied form. The next fuel we're talking about is also gaseous and quite well known, natural gas or methane. Engine engines running on this fuel are in the market for years already. These fuels or natural gas also enables quite low pollutant emissions. Currently, natural gas is of course also a fossil resource, so it's not CO2 free, also not from well to wheel, but it is currently very cost competitive also to other fossil fuels. And based on its molecular structure, based on the combustion, it can enable CO2 reduction of up to 15% compared to other liquid fossil fuels. And talking about synthetic methane, so making from renewables, methane, of course, is a quite simple molecule, but the Sabatier process we would use to produce methane from carbon dioxide and hydrogen is quite energy intense, so it's not the cheapest process or not the cheapest molecule you can choose. So it's a little bit more expensive than other e-fuels we're going to talk about. The good side, of course, is that natural gas is available in very large amounts today already. The grid is pretty much worldwide very well developed. So in fact, natural gas would be the only fuel that could be brought into the market on a very large scale, very fast, and effectively reducing CO2 emissions at least by 15% with current technologies. With that, we're coming now to the first liquid fuel. What would be methanol? Also, methanol is used as fuel already. Looking or from passenger car to heavy duty applications to deep sea vessels around the world. There are a couple of methanol powered vessels on the oceans already. I think it's roughly 5 to 7, somewhat in that range. The same announcements for methanol powered carriers are currently made. So within the next years to come, there will be more than a dozen of methanol operated vessels on the oceans. Methanol as such is available in more than 100 harbors around the world, also because it is an established product for the chemical industry and traded in roughly 100 million ton scale already. The methanol synthesis is also well known. Currently, it's mainly produced from natural gas and coal, but the process as such would not change if you would take hydrogen and carbon dioxide to produce then green methanol. The downside of methanol also is that it's considered to be toxic. In fact, it's not methanol as such what's toxic, but the metabolic products. Also, it burns with an invisible flame. So also here, handling safety installations have to be kept an eye on. It is anticipated that safety installations, of course, have to fulfill higher criteria as they have currently for conventional diesel fuel applications. So far, the applications for pure methanol operation are still limited. We do see a push from Asia mainly, both from passenger car, heavy duty applications, but also for maritime applications. And since methanol is a liquid energy carrier, that is very easy to store, easy to transport, we think that methanol will be used to really import and export green energy in a liquid way. And for that reason, methanol will surely have its place in future transport. The derivative of methanol is DME, dimethyl ether. Its physical characteristics are somewhat similar to LPG. So you have to pressurize DME to around 5 bar to get it in liquid state. But simultaneously, it's got a C10 number quite like diesel. So for that reason, DME has been investigated around the world, from passenger car applications to heavy duty applications, and also for shipping applications, like in the research project shown on that slide. They produced DME on board via methanol reforming with a technology provided by Holzapfel. And they used it in a only very slightly adapted diesel auxiliary engine to operate the auxiliary devices on board directly. So overall, DME is used worldwide in different applications. So for the United States, there's a fuel standard available already. Volvo investigated this intensively. Currently, from automotive side, Ford is significantly pushing this fuel type, also trying to certify DME as fuel over here in Europe. In Asia, DME is used as cooking gas quite broadly, like we do it here with kind of LPG. Overall, DME features a really quite clean diesel type combustion. The add-on costs for the engine are quite small. Adaptations you have to do are quite small. So DME might also be an interesting fuel, but the availability of DME apart from industrial sites is currently still very, very limited. Coming to infrastructure and availability of infrastructure. So the best fuel you could think of would be, of course, a fuel that you can directly use in today's infrastructure without any change. And there's pretty much one fuel that fulfills the criteria, and that are paraffinic diesel type fuels produced via the Fischer-Tropsch process. Fischer-Tropsch diesel are kind of drop-in fuels for all diesel applications worldwide. The downside is that the Fischer-Tropsch process is also quite energy intense, and that makes Fischer-Tropsch fuels to be at the upper range of the fuel production costs, actually. The technology as such is widely known and robust for quite more than 100 years already. And for Fischer-Tropsch fuels, you might also have more customers at hand, because Fischer-Tropsch fuels are the only liquid fuels that also can be used in aviation. So once ramping up that technology, for sure, there will be a customer at the end buying the product. Still, when you're looking at the fuel costs, where TCO are of highest importance, Fischer-Tropsch fuels for sure will not be an option. But thinking about yachts, for instance, that have to be refilled every now and then, other leisure boats, or if you have backup power generation, then Fischer-Tropsch fuels might be a very viable solution. So now you might say, okay, fuels are not available. We have had a question pointing in that direction previously. Of course, the fuels currently are not yet available in large scale amounts. The main reason behind this is that there's no one along the value chain who would actually really benefit currently from using or producing synthetic fuels. So politics around the world have to create incentives that there will be an invest in producing of such synthetic fuels. But still, we see that there are more and more announcements made. Synthetic fuel production will ramp up. On the left side of that slide, you can see a figure coming from Fuels Europe. They state that within the next 30 years, we would be able to have 100% of the non-electrified road transport be fueled with CO2 neutral synthetic fuels. And also the target that Andreas pointed on, 50% CO2 reduction for maritime and aviation by 2050 will also be possible by means of synthetic fuels if there would be an incentive to really start off the investments. Of course, talking about investments, investments we would have to take are significant and are really high, but compared to an all-electric propulsion across all applications, it's still cheap with an anticipated investment of somewhat in between 400 to 650 billion euro. On the right-hand side, you see the screenshot of an announced project that is ongoing already, that gained quite high interest in media. That's the Haruoni project located in Chile and run by Porsche, Exxon, and Siemens Energy mainly. They will produce within 5 years from now 550 million liters of synthetic gasoline fuel. I think that is a significant number for a single demonstration project. And we know that there are other large companies also from the old coast that are currently exploring the possibilities and business cases to really ramp up synthetic fuel production. Blueprints for such facilities, of course, are on the desks already. So in addition to the critic that the fuels are just not available. We often hear also the critics that e-fuel production is inefficient. Where should all the energy come from? Of course, making directly use of renewable electricity in the powertrain would be more efficient, but often that is just not possible. You can't electrify all the propulsion systems we do have. And obviously, we are not lacking energy in the world. We just have to make use of the sweet spots like Australia, MENA states, and for photovoltaics, Chile, for instance, for wind power. And given the average solar radiation and photovoltaic efficiency, on the right picture, you can see a blue square, and that blue square would be required for photovoltaic installation to cover the total electricity demand of the world by 2050. So in my view, a rather small spot if you compare to the world landscape. If you're now going to the extreme and saying, okay, all the energy consumed in the world by 2050 has to be provided by e-fuels. So all the landscape required for hydrogen production, for running the facilities and whatsoever, that would be equal to the 4 wet squares you see. You see that very much in the Sahara Desert. You would of course split that to different regions of the world. I said already, Australia, North America, wherever. Still, the required landscape equals 1% of the total landscape we have in the world. 0.3% of the landscape we have in the world, or 1% of the landscape that is currently used for agriculture. So definitely, we are not lacking energy. That wouldn't be a problem. What might be more interesting than the efficiency is, of course, the price and the cost. That is where it all ends with. Of course, synthetic energy carriers or synthetic fuels will be more expensive than fossil ones, at least looking from the perspective we are having now. This will not easily change unless politics will create incentives like taxation on fossil-based CO2 emissions. This is currently popping up, and we expect that this is getting more stringent, that the CO2 price is going to be increased. This then directly will be an incentive for making use of synthetic fuels or of green fuels. Looking at the fuel production cost for fuels just discussed, we see that hydrogen, of course, is the cheapest one with possible production cost of way below €1 per liter diesel equivalent, followed by methanol and ammonia. And compared to fossil fuels, the costs are currently somewhat doubled or even tripled. But this for sure will change after 2025, what that picture is actually belonging to. And based on this chart, you would say, of course, we're going with hydrogen, the cheapest option we can get. But as I said before, it's very likely that we will import green energy and that we will ship green energy around the world where we cannot make use of a DC-DC cable. And taking into account shipping, like shown at the lower figure on the right-hand side of the graph, the picture might change a little bit. And this is given over here in this slide. Here we have compared the production and shipping costs for green hydrogen and green methanol. And for methanol, we have also looked into different CO2 costs. So to subtract that from a point source or from the air or whatsoever. Whereas production costs are displayed in the bar graphs in black over here, the transportation costs are shown in orange. And obviously for hydrogen, what is in all the bar graphs, the left-hand bar, we see that the orange bar is very high for all investigated transportation routes, meaning that the shipping costs of liquid hydrogen are almost equaling the production costs. So in total, roughly doubling the costs at destination compared to production. And this is mainly due to the reduced energy density, the reduced volumetric energy density of hydrogen, and the high energy intense liquefaction process one has to take. Overall, up to CO2 price of about €100 per ton, methanol can be shipped around the world at even lower prices than liquid hydrogen. So also that one should take into account when talking about what fuel to use and where to produce energy and where to actually use energy in what form around the world. So now you can ask what fuel to use. Yeah, what fuel is the best? Andreas also touched on this question before slightly. We've tried to rate the different fuels by different characteristics, and as you can see, depending on what feature is utmost important for this specific application, the fuel to choose might be a different one. Thus, there definitely is not the one fuel what you have to choose. It is really directly depending on geographical boundary conditions, on fuel availability and infrastructure. How important is the energy density on board? Are you connected to a gas grid for stationary applications? Yeah, so it's really very, very depending on the boundary conditions of the applications. Still be sure that there will be a wide variety of different fuels in the future, and most likely even more diverse than what we use today. There's no one-fits-all solution, no one-fits-all fuel. It really comes down to choose the fuel or the best fuel for the specific application. With that, I'm done with my presentation. I thank you very much for the attention, and I'm sure there are some questions, Stefan.